Hi there, welcome to another version of the electric BMW 320i project. Well, getting closer, still working on a lot of electronics. So today I'm going to show you just what I got done with the latest version of the BMS. Finally got everything in the right place and working, and I'll show some test results of that. Also still working on my instrument cluster and how it's being driven. I'll show a few things about that. And then finally I have a procedure for replacing a connector that's on this Delphi 2.2 kilowatt DC-DC converter that Jack has shown. The problem with that, one of the connectors that it comes with, Amphenol connector, is that it's just not attainable anywhere. It's probably something special built, ordered and made just for that company. So I'll show how that can be replaced with a standard Amphenol connector and a few other things. So let's take a look. Alright, here we have finally the new version of the BMS, which has everything correctly working on it. This has, just as a review, has 4 channels of thermistor measurement and 4 channels of isolated voltage measurement. And it's designed to basically measure the different segments of a battery. It doesn't have to be all the same. I'll show you a picture. This is how I plan to deploy it in my car, having these various points to pick off the voltage and temperature. It has some unique features on it. Part of the isolation is this really great chip that is a combined opto-isolator and MOSFET switch all in this one package, and that's how the isolation between the battery segments is obtained. The system basically has a program that just goes through and turns each MOSFET on individually and each switch so that only one battery segment is measured at a time and the rest are all isolated from each other. And that's the only time when there'd be any measurement of current. And it's designed to actually have a 50 kilo ohm resistor right at the battery terminal, so there's really no high voltage that's being brought back to this unit. All the voltage will be dropped across that 50k resistor. It's based on the cinch enclosure method. Very nice, very strong sealing system. Uses a new type of connector. Again, it's got the same kind of crimp pin that the amp seal does, but this one you have to plug it in and then tighten the screw down, and that's the only way you can get it on, is by tightening that screw. So I'll show you this running and how I'm able to test it out. This is how the connector goes on. You just have to line it up, bring it in, and then put a wrench on it. Takes a lot of turns, but it comes up and makes a nice seal. And just like the amp seal, there's a gasket in here that seals the wires, and then this makes a positive seal against the pins, and then the whole thing has a gasket around it. Makes a nice water seal for the whole thing to be IP67. Here's a look at the test setup I put together for testing out the BMS. So I have this made up the 18-pin harness, and then brought that over to these barrier strips where I got 4 thermistors set up, and then I have a voltage divider set up to simulate different battery sections. And I have a little program running that accesses all the 4 temperatures and all the 4 batteries. And temperature, you can see, is very accurate and repeatable. It's across the 4 that are just sitting there in air. And then the battery voltage is a multiplier, just to say, you know, that would be approximately what the segment of the battery might be. It's just the same multiplier across all, and just the variation of the resistor tolerances, probably just some of the voltage that's seen there. But it seems to work pretty good. I'll show you this calibration I did on the thermistor. It's very typical. Shows the nonlinear curve of resistance versus temperature. But what was really kind of interesting was I found if I took that resistance and I plotted it using the Steinhart-Hart equation and coefficients, and then I took that value of temperature and plotted that against the voltage, that it's not linear, but it fits a 3-point equation polynomial very well, and that's a pretty easy thing to deal with even in the Arduino code. And that's what I'm using to calculate the temperature that was shown on the screen that was coming through from the serial console. So it looks like a pretty good system. Now the only thing that's left is to connect up the CAN bus and bring the cab 300 data in through and make that all part of the operating system for this board. You may remember a while ago I was doing spoofing of my instrument cluster, and here's a picture, shows the whole cluster, and I was just spoofing the tachometer. Well, you notice in the middle of the tachometer there's what appears to be a digital clock. Well, I thought that might make a really nice way to display other information besides clock. So I looked into it, and I think at that time I also showed about this nice little 4-digit 8-segment LED display, which was almost identically to the size of the one that's in the that was inside that tachometer. And so here you see the actual unit. Pretty amazing. Back then they required this giant silicon chip to just do a clock function, but it is, how they did things. And so fortunately the size of this little display here is exactly the size of that one from SparkFun, and I'll show you how that went together and what I can do with it now. So here you see the tachometer instrument, and what I've done is cut out a PCB the same size as the one that had the old clock module on it, and mounted the new 4-digit LED display from SparkFun, and that just slides back up in here. So it's got nice hardware on here to lock it in place. Okay, so I got the circuit board back in there. It doesn't go in that easily, but it's good because it's held in really tightly. Not likely to move around when it's in the car. So have a little Arduino Uno that I programmed to control that display, and you'll see basically it goes through the first one is voltage, and then amperage, then the amount of battery capacity, the energy being used, and then the clock, and then temperature outside, and then also you can have it show the RPM. What's interesting is you can see this on the video, but you can't see this by eye, is the refresh rate of that LED display that's being shown up on the video. But by eye you can't see that, and this just loops again through it. Because it's only 7-segment, it has a limited number of fonts, so I just had to pick different things, like the U there is for volts. You can do an A for amps. C would be for state of charge. E for energy, which would be kilowatts. Time, and then you can do also an F for temperature. So it should be a nice way to drive all of the gauges, and then have the ability to switch the different messages on that little LED. There was originally a little setup, goes right on the dashboard, has the buttons to change the time, but that little momentary contact button can be used to change the mode on this little display and show different information. Hi, I'm going to show you something about this wonderful 2.2 kilowatt Delphi DC-DC converter that Jack has available. Unfortunately, some of them come with this Amphenol connector, which is totally unattainable anywhere. And so I looked into that and thought, well, you know, there's nothing special about that. It is unique in that this one that's here is a push-on type, and probably was, you know, some car manufacturer had that specifically made for them. But there's nothing very special about it. It's just a 2-pin connector. So I looked into what was available through Amphenol, and just their regular standard run-of-the-mill 2-pin connector. And the specs on this are, it's actually rated 700 volts and 13 amps DC. So more than enough for what's needed to put into this at 2.2 kilowatt. Another alternative for replacing this connector is available from New Eagle, and I'll show you that website. They have a whole kit that they'll sell you, and it basically has the recommended or the other type of connector that Amphenol made, specifically a high voltage connector. But unfortunately with New Eagle, to buy that connector, they want you to use some type of instructions that they have, and then they require you to sign a non-disclosure. So I don't know if you want to go down that road, but what I can tell you about that connector change is that it actually, part of this area here has to be machined to accommodate it. So to do that, you're basically going to have to take this whole thing apart and to take it in the machine shop, because I would personally not put this in a end mill and have chips being cut with all the electronic components in here, with the possibility of one chip getting in there and shorting things out. So I think going to the standard Amphenol connector is probably the best way to go, and I'm going to show you how I did that. Okay, the first part of replacing the connector is to take the cover off, because you have to remove the wires that are on the inside. I'll show you a little computer graphic that shows that inside. These top bolts are all a T25 star. So let's take them out. Okay. Probably a gasket underneath there. Nice little O-ring. So here you can see the inside piece. These two wires have to be disconnected and soldered to the new connector, which is this little amp seal. Okay, the cables on the inside, they're held down by a T20 star screw and a lot of torque. And then the front connector comes off. That's a T10 star. there you go. Looks like it was all, it's a molded assembly. It's potted on this side, probably just to help everything stay nice and dry, non-corroding. We'll probably have to get some different wires. But this little lamp seal connector, it's exactly the same bolt pattern size. Go right on there, just like that, and be pretty much easy to mate up the standard 2-pin connector. They have a lot of different types of strain reliefs available. I'm even thinking there's a right angle one, which might be better to have this come out and turn down. One thing I did think about was maybe getting these powder coated bright orange, like for high voltage, since that seems to be the going theme. But this seems to be going to be a pretty easy replacement. Okay, here the pigtail's done, soldered on the wires. Probably could use 16 gauge here. That's what the pin size is, but I only had 14 gauge with the silicone jacketed wire. So next thing is crimp on the connectors and the heat shrink. So there you go. Here's the one that came out. Here's the one that's going in. I think it'll work just fine. So probably replace this gasket. So I did get a new one and put it all back together. Alright, now it's installed. See right here. Same wires, same connectors, screwed right down. Should be ready to go. Let me put the lid back on. It's a nice O-ring gasket. Just line up the holes and there we go. Now go back and torque them all in. Done. Well, here I almost have everything ready to test it. Got the cable made up. I have a full wave bridge rectifier, high voltage fuse, and little capacitor bank just to be able to have a decent DC signal going in. But as always, Amphenol's the trouble. Got to make up that connector. Got to make up another one to go to the JevQ, and then I'll program it up and see how it works. So maybe that will be for next time. I don't know if how many of you seen this, but Charge magazine that just came out this month had a very interesting article on the cold weather effects on all vehicles and the impact of plug-in vehicles specifically. And what was very interesting was they had a lot of leaf data, because I guess they must have been tracking some particular fleet. And I thought it was very interesting because the curve that they showed exactly looks like the curve that I experienced in my car, and that I'll show you this curve here. Basically, yeah, when I'm at nice 25 degrees C, or nice balmy weather, which I haven't seen in this part of the country for a long time. Yeah, I get like 80 miles on a charge. But like this week, when it was say 15 degrees in the morning, that drops down to like 45 miles. Yeah, it's really, really tough. And yeah, they do talk about things like preheating. Is like on the Leaf, it will use the if it's plugged in the charger, it will use some of that power. But it really doesn't help. The heated seats do help. Heated steering wheel helps a lot too, and a really heavy jacket. So just one of the things that unfortunately in the northern climates, it's really tough on electric vehicles. So it's great to finally have that BMS all working. I'll have to see. I hope we don't have to do another spin of that board, but we may be able to get that into production, and it will be available for sale sometime soon. Of course, you never know how long it takes to get through fabrication in China, but we'll see what happens there. Again, really cool thing with my dashboard that's coming together in the instrument cluster. I'll just have to see what else I can do with that. I know David Seabury has worked on a really nice driver for the rest of the gauges, and maybe next time I'll show that being used on powering up and running all the gauges simultaneously. And well, next time also probably show testing of that 2.2 kilowatt DC-DC converter. I just couldn't get all the parts together. Mostly making up the amp seal connectors is very time consuming, and I just couldn't get that done before I had to get this video together. So also maybe next time we'll actually start putting batteries in the car, since it's starting to get warm out and the snow is finally melting. Might actually be able to drive it in a month or two. So thanks again for watching, and I'll catch you again.